Hi, my name is Amin, and I'm one of the SIs for Professor Maduro's BIO005A class. And in this video, I'll be giving a brief overview on topic 3. So to start off with, I'm going to start off with the Miller-Uri experiment. And Miller-Uri started off with small molecules such as water or CH4, molecules that they knew that pre-existed in the Earth. And they created a closed system to emulate the Earth. So they had electrodes for lightning, they had heat, and various other functionalities. And they realized that over time, these small molecules turned into larger molecules, such as amino acids or nucleic acids, things that are found in living organisms today. So why is carbon, why do we call it the carbon-based life? So this is because carbon is very versatile. So carbon can form bonds with up to 4 different atoms. It can form double bonds, it can form single bonds, and even triple bonds. So these combinations can create different structures, which lead to different physical and chemical properties. So many times in this class, we're going to refer to hydrocarbons. And hydrocarbons are compounds that have a mixture of carbons and hydrogens. So there's 2 types that you will be talking about in this class, alkanes and alkenes. So alkanes are carbon-to-carbon single bonded chains, so they only have single bonded carbons. And they're referred to as saturated because they only contain single bonds. While alkenes have carbon-to-carbon double bonds, and even one double bond will make a carbon chain or a hydrocarbon called an alkene. And they're referred to as unsaturated because they have a double bond. And so a key component to remember is that hydrocarbons are hydrophobic. And why is this? Well, it is because all electrons are equally shared, making every bond nonpolar in a hydrocarbon. So this makes it hard for it to mix with water, which is why you see that when you mix oil with water, it doesn't really mix well and it actually forms like oil droplets in it. And so these hydrocarbons can get very long, and writing out an entire Lewis structure will get really complicated and messy. And so what we like to do is write them in line bond structure. So all the carbons are represented in this line, and every point or angle represents a carbon. And since we know that carbon can be bound to 4 different atoms or 4 atoms, we can assume that whatever bonds we don't see are hydrogens. So if we look at this carbon right here, we can see that it's bounded to 1 carbon with this bond right here. However, since there's 4 things possible, 3 other bonds would be hydrogens, as seen right here. Moving to a little bit more complicated structure, we can see this one down here. There's 3 carbons, 1 here, 1 here, and 1 here. The carbon on the left has 2 bonds, right? Because it has a double bond. And the other 2, to make it 4, would be hydrogens. So if you can see right here, you got 2 hydrogens. The middle bond has 3 bonds on it. The middle carbon has 3 bonds on it, 1 bond here, and 1 double bond. And so it can only have 1 hydrogen attached to it, making it a total of 4. And a big thing to remember is that only carbons and hydrogens disappear. So all other atoms have to be spelled out. So if your compound has bromine or oxygen on it, you have to write Br or O. You can't assume that they're there. So this leads us into our next topic, which are isomers. So isomers share the same chemical formula, but have different structures. So if you look at structural isomers, they both, in this case butane, they both have C4H10, right? However, butane has a straight carbon chain of 4 carbons, while isobutane has 3 carbon in a chain, and then it has 1 carbon over here. However, both of their formulas are C4H10. Cis transisomers refers to the geometrical displacement of the atoms. So if you look at X over here, these are like 2 of the same atom, so we can say, let's say they're chlorines. And in the cis isomer, they're both on the same side, while on the trans isomer, they're on opposite ends. And finally, enantiomers, they can get a little tricky, but a big thing to remember is that enantiomers occur when the carbon is bound to 4 different atoms. And so they're actually mirror images and are non-superimposable. So what this means is that if you take your left hand and you put your right hand over it, you can see that they're non-superimposable, right? Because you have 2 thumbs sticking out. However, if you put them like this, like in a mirror, you can see that it matches up perfectly. So technically, they're not the same, but they're enantiomers. So in this case, if you look at the molecule on the left, you can make that your left hand, and the molecule on your right can be your right hand. And you can see that if you put them on top of each other, they won't be the same. But you can see that the NH2 and the H are actually mirroring each other in this picture below. And this leads us into our next concept, which is asymmetrical carbons. And so we gotta remember, a rule of thumb with asymmetrical carbons is that the carbon must be attached to 4 different atoms. So the best way to explain this is going through examples. So let's look at this one on the left right here. There's 6 carbons, so we'll start with carbon 1. Carbon 1 has an H, a double bonded O, and a carbon chain attached to it, right? So that's only 3 things. So since it's not 4, we cannot call it asymmetrical. Now let's look at carbon 2. Carbon 2 has an OH, it has an H, it has an aldehyde up here, and a carbon chain down here. So since those are 4 different things, we can call carbon 2 an asymmetrical carbon. Similar situation with 3, 4, and 5. They each have 4 different substituents, which make them asymmetrical. However, carbon 6, you can see that since there's the H2 over here, those are considered 2 of the same atom, which doesn't make that asymmetrical. So there would be a total of 4 asymmetrical carbons on this molecule on the left. So let's look at the molecule on the right. We'll start with carbon A. Carbon A is aldehyde, similar to the one seen right here. And we can see that there's only 3 things attached to it, so we won't call that asymmetrical. However, if we look at carbon B, we got an OH, we got an H, we got a carbon chain here, and an aldehyde here. So those are 4 different things, and we can call that carbon B asymmetrical. Carbon C, D, and E have multiple H's. There's 2 here and there's 3 here, which make it, so you can't call it asymmetrical. So next we'll jump into functional groups. So one of the functional groups you guys talked about was hydroxyl groups, which are notably like the OH. And these are found in alcohols and carbohydrates. And since the OH bond is very polar, you can form hydrogen bonds. On the other hand, there's carbonyl and carboxyl groups. So carbonyl groups are referred to as your ketone and your aldehyde. So these 2 on the left. And you can see that a ketone has a carbonyl, a C double bond O, to 2 different R groups. So in this case, we see carbons. While an aldehyde has a C to an O with a carbon and 1 hydrogen. So this hydrogen is very important to make an aldehyde. While a carboxyl has an OH on it. So this is also referred to as a carboxylic acid. And carbonyls and carboxyl groups have a very special property that they're very polar because of the C double bond O, and they can also participate in hydrogen bonding. So where do we see this in like molecules and living organisms? We can talk about glucose, and you can see that this first carbon over here is actually an aldehyde because it has an H and a carbon on this side, while these OHs over here can be called hydroxyls. Moving further, we'll look at amino groups, which are characterized as NH2. And NH2 groups are polar, and they also can hydrogen bond. And a big thing is that nitrogen is able to attract H+ ions in water, which make that solution more basic. So what happens is since NH2 is able to become NH3+, since you're removing H+ ions from the solution and putting it into NH3, you're increasing the basicity of the solution. So essentially, NH2 will make a solution more basic. Finally, we have sulfhydryl, so SH, and these are also polar, and they're found in amino acids, specifically this one, cysteine. And something notable is that in this amino acid, you can also see that there's an amino group over here, which is why it's called an amino acid. And the acid component of it comes from this carboxylic acid. And the R group on this amino acid is a sulfhydryl group. Finally, we're going to end with phosphate and methyl. So phosphate groups are polar, and they're found in DNA, RNA, and ATP. So in DNA and RNA, they make up the backbone, while in ATP, they're the triphosphate in the name adenosine triphosphate. Finally, methyl, these are referred to as CH3. They have similar characteristics to hydrocarbons as we saw before, in that they are nonpolar and they're hydrophobic. However, something that Professor Maduro talked about was that DNA has thymine while RNA has uracil as one of its nucleic acids. And the primary difference between the two is this methyl group right here. So DNA has thymine and it has this methyl group, while RNA has uracil and it does not have a methyl group. And that is all. Thank you for listening and good luck this week.